Hey guys, today I'm going to talk a little bit about the theory of ICM and bubble factors. So the basic theory of ICM is that in a tournament, the chance of finishing in one of the top places is directly proportional to the relative size of a player's chip stack. And ICM models try to quantify that idea. Several different models have been developed over the years, but they all work conceptually as follows. First, they build an elimination tree, which is a tree of all possible finishing scenarios. So I've drawn one here for the 3-player case. What we see here is that in a tournament with 3 players left, these are all the possible ways in which that tournament could play out. Player A could be eliminated first, and then given that player A has been eliminated, either player B or player C could be eliminated next. And then there's one player left, and that player wins. Or player B could be eliminated first, finish in 3rd place, and then either player A or player C could be eliminated next, and in each case the other player finishes first. And finally, player C could be eliminated first, player A or player B could be eliminated next, finish in 2nd place, and then that determines the 1st place finisher. Now, once we have this tree of all the possible futures in which this tournament could play out, what we need to do next is we need to assign a probability to each of these futures. And this is where chip stacks come into play. So for this first level, we will start with the chip distribution that we put in here. So we say player A has 1500 chips, player B has 1000 chips, and player C has 500 chips. And then we use a formula to determine, given this chip distribution, how likely it is that player A is eliminated first, how likely it is that player B is eliminated first, and how likely it is that player C is eliminated first. And in this case, with this chip distribution, where player A is the big stack and player C is the small stack, it will be most likely that player C is eliminated first and least likely that player A is eliminated first. Once we've done this for the first level, we then need to assign probabilities to the next level. So, given that player A has been eliminated first, what's the likelihood of player B being eliminated next, as opposed to player C being eliminated next? And since these probabilities are based on the player's chip stacks, what we need to do is, in this subtree here, we need to distribute player A's chips, since we assume on the next level that player A has been eliminated. We need to distribute player A's chips among players B and C. And then we can use the updated chip stacks for B and C to calculate the probability of B being eliminated next or C being eliminated next. And similarly for the other subtrees. So in this subtree, we need to distribute player B's chips among players A and C. And in this subtree, we need to distribute player C's chips among players A and B. And we'll use another formula to determine exactly how chips are distributed among the remaining players when a player gets knocked out. So the way in which ICM algorithms differ is by exactly how they define these two formulas for elimination probability and for chip redistribution. Okay, so now we have this tree and we've added the probabilities to each node, and we can collect all of the paths from the root to one of the leaves, and that's all the ways in which a tournament can play out. A third, B second, C first, A third, C second, B first, and so on. And we can just multiply the probabilities of each node on a path to get the overall probability of that outcome. For example, the probability of this first outcome here is the probability of A finishing 3rd times the probability of B finishing 2nd. So finally, to get the ICM equities, we look at each possible outcome and we look at the payout table for the tournament here. And then we just assign to each player the payout for the place in which he finishes in each outcome. So for example, here in this first outcome, player A gets nothing since he's eliminated first. Player B gets 35% of the prize pool and player C gets 65% of the prize pool. And we do this for all the possible outcomes and multiply in each case by the probability of the outcome. And then we sum up all these probability weighted equities, and that gives us our overall ICM equity. Okay, I hope I managed to explain what ICM equity actually means and to give you an idea of how ICM algorithms work. Let's talk about bubble factors next. Bubble factors are a concept introduced in the book Kill Everyone by Nelson, Stripe and Heston, and they give us a way to adapt the notion of pot odds to tournament situations. As you may recall from the ICM overview video, it turns out that in ICM situations, losing chips will decrease your ICM equity by more than winning those same chips would increase your ICM equity. And bubble factors capture the strength of this effect in a single number. Bubble factors are opponent specific and are defined as follows. Assume you went all in against that opponent. Calculate the change in your ICM equity if you win and the change in your ICM equity if you lose, and then divide the latter by the former, that is, divide the cost by the profit. And that's what the ICM module has done here for each opponent. For example, this tells us that when player 2 plays against player 1, the chips that player 2 is risking are more than twice as valuable as the chips that player 2 is hoping to win. Bubble factors give us a really nice overview of ICM dynamics. We see that the big stack doesn't mind playing pots with the short stack, but the short stack also doesn't mind playing pots with the big stack too much, though he preferred to play with the medium stack. The medium stack, on the other hand, really doesn't want to play with the big stack, so that's who the big stack should be targeting. And bubble factors also let us adjust pot odds for ICM pressure. To calculate your tournament odds, you divide your pot odds by your bubble factor. For example, when facing an all-in from the big stack, the medium stack is getting pot odds of 1-to-1, ignoring blinds and antes, and would normally need about 50%, 1 divided by 2, equity to call. But since he has a bubble factor of 2, his tournament odds are 1/2-to-1, and he therefore needs 66% equity, or 1 divided by 1.5 to call. Similarly, if player 2 was in the big blind facing a min raise from player 1 in the small blind, he'd usually be getting pot odds of 3-to-1, hence needing 25%, or 1 divided by 4, equity to call. But with a bubble factor of 2, his odds are only 3/2-to-1, and the equity needed is 1 divided by 2.5, or 40%. To call a pot-sized post-flop bet, odds of 2-to-1, he'd need 50% equity, rather than the usual 33% equity to call. Alright, I hope you enjoyed the theory of ICM. Best of luck at the tables. Cheers and goodbye.